And yes, one more important thing. So since there's a lot of 21 guys and all, I'll let you know this, right? So if you could cover these four lessons, right, perfectly, and like waves and oscillation means like waves, oscillations, and light optics also, right? So and then thermal as well as electricity, right? If you could get these things done, right? So like you'll be definitely getting the first essay from essay mechanics. So second question is second means like the essay, right? So mostly it's going to be waves and oscillations or else light optics, and there's another thermal question as well as an electricity question, right? So 100% if you get that done perfectly, right? So you can score a large content, large amount of marks from the second part, right? So second lesson, like the second part B essay paper, right? And also when it comes to the structure, right? So experiments. So you guys know. So the first experiment is mostly going to be mechanics, from mechanics, and the first unit, that is units and dimensions, measuring instruments, right? So mostly it's going to be mechanics, right? So measuring instruments, there's five instruments, right? So if you are okay with that, and like there's a set of experiments in mechanics, so that will be the first one mostly, right? So I'm talking about most appropriate, most probable thing which might take place, right? So and the second one is mostly going to be experiments from this waves and oscillations or else optics, right? Waves and oscillations or else optics, right? And third experiment is going to be on thermal, right? So mostly like 80 to 90% it's going to be from thermal physics, right? So and the fourth experiment is mostly going to be from electricity. So one or two questions were there from electronics. So in the recent years, not completely, they have included electronics also, one or two parts, but it's mostly going to be electricity, right? So if you can get these things done properly, right? If you get these things, four things done properly, so the second 50 marks, so first 50 marks is for MCQ. So the second 50 marks, from the second 50 marks, so most of the marks could be collected, right? So therefore, always give a higher priority to these lessons, right? So this is my opinion, right? So like, if you are very bad at electricity, you can go for electronics, right? But then you miss this, right? So if you are bad at thermal, you can go for matter and radiation, but you'll miss this, right? So therefore, that is why I mentioned always. So make sure to get these things done properly. So therefore, the second, like you won't have to put a lot of effort to cover the second lesson, the second part of the paper, right? But MCQ, of course, can't help, right? So like all the content is going to be there, right? So and also a lot of content is going to be from these four lessons also: mechanics, waves, and thermal, electricity, right? So larger part of the paper could be covered if you get these things done, not overall, right? So I'm not talking about overall, 100% done, right? So perfectly, you need to cover it perfectly with 100% theory, right? So because like you can't answer a paper, essay paper, just having an overall idea, right? So like that's not going to be possible. So make sure to, like, if you are learning a certain lesson, targeting, right? So make sure to get that done perfectly, right? So yes, all right, I will start this session. Right. Main topic is going to be waves and oscillation. Waves and oscillation, right? So the main topic is going to be waves and oscillation. So guys, if you don't mind, can you guys just mute,
Recording in progress.
mute your mics because like it could be,
No need, no need. No need.
yes.
Adib,
Yeah, sorry. I'll mute it.
Yes, okay, that's fine, right? So that's okay, that's fine. Because like it's not an issue for me. So for others, of course, like it will break their concentration. Right? So that is the issue. If not, it's fine, perfectly fine. So yes, the main topic is going to be waves and oscillation, right? So let's see. So it's going to be waves and oscillation. So what is waves and what is oscillation? We need to have a perfect idea, right? So let's see. So let's consider, first of all, let's consider a water surface, right? So let us consider a water surface, right? And let's consider a water surface and also consider another a rod, right? So kind of a rod, right? And let's like perform an oscillation. Let's perform a repeated motion. Let's perform a repeated motion, right? So let's dip this inside as well as take it out, right? So when you keep on performing this kind of a motion, this is an oscillation, right? So this is an oscillation, right? So we'll come to what an oscillation means and all in a while, but the general idea is when you repeatedly perform the same motion, it's going to be called as an oscillation, right? So when you perform an oscillation by using a rod, right? So what's going to happen next? So obviously, water wave is going to start to propagate, right? So a water wave is going to start to propagate, right? Yes, a water wave is going to start to propagate, right, along the surface of the water, right? So if you analyze this properly, you'll see that a wave, yes, a wave was generated due to an oscillation, right? A wave was generated due to an oscillation. When you do this oscillation, due to this oscillation only, the wave starts to propagate in the forward direction, right? So therefore, what should we learn first? Is it the wave or else the oscillation? Should be the oscillation, obviously, right? So because of the oscillation only, a wave starts to generate, right? So first of all, we need to analyze about oscillations, right? So therefore, in our syllabus content, so we are going to first of all analyze oscillation. We are going to finish oscillations, and then only we are going to move on to waves, right? So that is how it's going to be done. And so let us take another example, right? So like consider a guitar. Consider not a guitar. Let's consider a string which is clamped at two pegs. So let's consider two pegs, right? And let's clamp a stretched string, right? So from one end, let's start to pick it, right? So if you pick this up from one end, what will start to happen? So like what you do is like you start an oscillation by plucking this, you start an oscillation, right? So when you start an oscillation, when you do that, right? When you do that, what happens is a transverse wave, right? A transverse wave starts to propagate along the string, right? A transverse wave is going to start to propagate along the string. So which means, once again, this wave started to propagate due to the oscillations, right? So first of all, we will have to talk about what an oscillation is and the things under oscillation, right? So yes, I guess that is clear, right? Okay, fine. So before we move on to the oscillation, the next main topic is going to be oscillation. So before we move on to the topic oscillation, let's take down the required things as quick as possible, right? So, and make sure to write quickly. That's like we're going to. The thing is, you need to have a rough note, right? So it's not like it should be very neat and tidy, right? Somewhat a clear note, right? So yes. So put the main topic: waves and oscillations. Waves and oscillations. Waves and oscillations. Waves and oscillations. Waves and oscillation. So below that, start writing. Start writing. A wave always generates. A wave always generates. A wave always generates as a result of oscillation, as a result of oscillation. So just draw this. Just example, draw this. Example 1. Draw this. Only this.
Sir, could you just quickly go through that first example, please?
Yes,
Like how-
all right, sure. Yeah, sure. The thing is, it's like this, right? So like, assume there's a rod. So others, you can start drawing, right? So so this is what happens, right? So there's a rod, right? So by using a rod, if you start to perform the same motion repeatedly, right? So what might happen? So it's like when you perform the same motion repeatedly. So the terminology that's given is oscillation. It's considered as an oscillation, right? So when the same motion is repeatedly performed, right? So what you do here is it's an oscillation. So by using the rod, you are oscillating the water surface. Right? So when you oscillate the water surface, what generates is a water wave. As a result, a water wave will start to generate, right? So the thing that you need to understand from this is, for a wave to generate and propagate in a certain direction, there should be a oscillation done in a certain place. You need to oscillate, right? So this water surface should be initially oscillated at a certain place. Then only a water wave will start to propagate, right? So therefore, the thing is, before we move on to waves, we need to cover the oscillation part, right? So yes, that is pretty much it. And then also here it's the same. When we oscillate it by plucking the string, right? So a transverse wave will start to propagate along the string, right? So once again, as a result of oscillation, a wave generates, right? So therefore, the oscillation should be analyzed first, right? Yes. And I guess it's done. Right. So below this example, you can write down. I'll give you in detail. Right? So write down. When an oscillation is done, when an oscillation is done on the surface of water, a water wave starts to propagate. A water wave starts to propagate. A water wave starts to propagate. on the surface of the water, on the water wave starts to propagate, right? Propagate on the water surface, on the water surface, sorry, on the water surface, on the water surface, away from the point of oscillation, away from the point of oscillation, away from the point of oscillation. So you can draw this once again. Examples 2. These are very basic theory, but still let's bear it up for a while until we get into the main part, because without knowing the basics, it's going to be difficult, right? So this is a string, 2 pegs, right? Right. Below that, write down, when a string slash wire where the two ends are connected, where the two ends are connected to two pegs, pegs, P-E-G-S, pegs, is plucked perpendicularly, to the string, is plucked perpendicularly to the string, comma, a transverse wave starts to propagate away from the point of oscillation, away from the point of oscillation. Next point. Therefore, oscillations should be analyzed. Oscillations should be analyzed before moving on to waves. Right. So we are going to move on to waves, oscillations, right? So it will take some around maybe 3 sessions to cover oscillations, right? So we'll see. Right? So as soon as possible, let's cover oscillations, but we'll see, right? So oscillations. There's a lot to learn in oscillations, right? Oscillations. First of all, we need to know what an oscillation is. Right? Yes, we have heard about oscillations, and yeah, we know if the same kind of motion is performed, it's going to be called as an oscillation. Yeah, obviously it's true, right? So the main idea is, right? So the main idea is, if it is an oscillation, right? If it is an oscillation, within the motion should repeat. So the motion should repeat within equal time intervals. within equal time intervals, the same motion should repeat. Right? It's like this. So yes, a particle is there, right? So a particle is there, right? So it performs to the right, right? And once again, it performs to the left. Once again, to the left. Once again, to the right. So to perform this complete motion, let's assume it took 2 seconds. Let's assume it took 2 seconds. So this will be considered as an oscillation if and only if this particle performs the same motion once again within 2 seconds. First oscillation is done like when it performs the motion repeatedly. We usually call it as oscillation, but the exact idea of that is the motions are repeated in equal time intervals. So for the particle to move to a certain location and to return back, it takes first of all 2 seconds. Once again, if the same motion is repeated, once again, if it takes the same 2 seconds, then it can be considered as an oscillation. Right? So there's no issue. It can be considered as an oscillation. But if it takes 3 seconds, then yes, the same motion is repeated. It moves forward, but here, returns back. But if it takes 3 seconds, we can't consider it as an oscillation, right? We cannot consider it as an oscillation, right? Yes, I will come into that, right? So the next part is the simple harmonic motion. So yes, there's a difference, right? So I'll tell you what. Yeah. So this is oscillation. The basic thing is the same motion should be repeated. The same motion should be repeated within same time intervals. Within same time interval. So is this only like, is it the only kind of oscillation that could take place? No. Even this is an oscillation, right? So like, okay, there's a particle. This is also an oscillation. So what's wrong with this? Nothing. There's no issue because like it starts and returns back to the same place within equal time intervals. If it performs this same motion repeatedly within equal time intervals, this could also be considered as the oscillation, right? So motion of a pendulum, if it takes the same time and the same motion is repeated, it's an oscillation. It's an oscillation. There's certain other conditions like, so there should not be a resistance and also like these things like see later. So there's types of oscillations, damp oscillations, and all. So later, let's move on later for the time being. Right. So this is an oscillation. So what else? Examples. Motion of hands of a clock. And you take, so you might not have wondered about these things, like whether these are oscillations, but now you should know, right? So these are oscillations, or these are also oscillations because, okay, so the same motion is repeated and also the same time takes, right? So like for an hour hand, if it takes 12 hours to perform one oscillation, one motion, complete motion, and return back to the same place, in the next hour also it will perform 1 hour, like in the next oscillation, in the next complete revolution also it will perform, it will take 12 hours, like it's not going to take 13 hours, it's going to take 12 hours. So the same motion, same time interval. Once again oscillation, right? So like, yes, there's a lot of examples, right? So yes, I guess you know what an oscillation is. The basic idea is understood, right? Yes, let's take down the topic oscillation. 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 The main topic oscillation. Yes, below that right now. Within equal time intervals, within equal time intervals, within equal time intervals, within equal time intervals, if the same motion, if the same motion takes place again and again, takes place again and again, then it is referred to as, then it is referred to as an oscillation. An oscillation. Examples of some oscillations. Example, first one, motion of a pendulum. Motion of a pendulum. Motion of a pendulum. Second example, wire of a guitar. Wire of a guitar. Wire of a guitar. Motion of hands of a clock. Motion of hands of a clock. Motion of hands of a clock. Just mark these side by side, right? Smaller figures, right? The time taken to write notes and all these things, it's never a waste of time. Right? It's like even I can send you the note and then ask you guys to cover it, but it's not going to work. Right? So you need to write and then only it goes into your brain straight away. Right? So that is how psychology works. Right? I don't know. So as per my convenience, like as I know, of course, this is the best way, right? So to learn, the goal is to learn, right? So don't worry about the time. Okay? Whatever you learn, let's learn it perfectly. So done. Yes, right. So, okay. Now, we know what an oscillation is. So, the simplest form of an oscillation, the simplest form, like I'm going to give you a general idea, okay? So, this is not the definition. So, the simplest form of an oscillation, or the simplest motion of an oscillation is what kind of an oscillation? So what kind of an oscillation is going to be the simplest from these three? So yes, this kind of a motion, like rather than this, these are simplest forms of oscillation. Simplest forms of oscillation. Right? Why do I say it as this? As that it moves forward, it turns back, moves this side, turns back. So there's no issue with that. I mean, it's very, very simple, right? It's very simple. So rather than this, so to take turns and then once again take turns. So it crosses and that's an issue, right? So like rather than this, these are considered as the simplest forms of oscillations, right? So these simplest forms of oscillations are what, like, further categorized as what? Further, they are given a name as simple harmonic motion. They are given a name as what? simple harmonic motion. Right? Simple harmonic motion. But this is the general idea that I gave. It's not going to be the definition of simple harmonic motion. If a certain motion is supposed to be a simple harmonic motion, there are certain conditions to satisfy, certain definitions. So it's very complex. Right? So I just made all those complex things to like a very simpler form. So a general idea, get the general idea, right? So the simple harmonic motion. You guys might have heard about simple harmonic motions. Okay, this is a simple harmonic motion and all that, but simply a simple harmonic motion is the simplest motion of an oscillation. Simplest motion of an oscillation, which means like moves forward, return back. Right? The general idea. We'll see in detail what a simple harmonic motion in a while. Right? So yes, below that, right hand. The simplest motion of an oscillation is considered to be a simple harmonic motion. The simplest motion of an oscillation is considered to be a simple harmonic motion. A simple harmonic motion. So draw this once again. It's like this. It starts at x equals 0, right? Starts at x equals 0. It moves towards the right in the positive direction, where x is equal to r. The same r you need to take this side also. This is considered as negative direction. So x is equal to minus r. So don't try to complicate things. Just get an idea that. So like we will consider this right hand direction as the positive direction. So if this is the center point, so when you move towards the right, the displacement increases r. So at this point, the displacement is something around r. Let's assume something around r, right? R. So after it moves r displacement, it once again returns back. So it has moved what displacement? R. So towards the left also, it should move the same r displacement. Towards the left also, it should move the same r displacement, but since displacement is considered as a vector quantity, the displacement towards the left is considered as a minus displacement, and it is minus r. So these things are given certain names, amplitude and all. I'll come to that later. Just an idea. So just the general idea. So draw this, right? It's only this. Yes, minus and plus, right? So it's like this. So, whenever you deal with displacements, right? So whenever you deal with displacements, so displacement is what? Displacement is a vector quantity. It has a direction, right? So before you deal with displacement, you need to choose a certain direction as plus. It's up to you, right? So like you need to choose a certain direction as plus, right? So in that plus direction, if the particle moves, that means the displacement increases, plus displacement r plus r. So this is the direction that I chose as plus. This is the direction that I chose as plus. When the particle is moving from here to here, so I have chosen this as plus direction. So the particle is now, okay, it has moved here and once again returned back. Once again it's returning this direction, So the displacement is what? It's going to be minus. displacement is going to be considered as minus, right? So this is the origin. We consider this as the origin, right? Origin, the center point as the origin, right? Where the symmetric, where the motion is considered the symmetric of the motion, right? That is the origin. So these things we learn in a while in detail, right? So mark this as origin. Origin, right? Origin. From the origin, left, right side towards the origin is considered as plus. Usually, it's sign conventions, right? So it's like standard is towards the right. We consider plus. Like the displacement when the particle moves in the right hand direction, we consider it to be having a plus displacement, and from this point, if the particle moves towards the left, we consider it to be as having a negative displacement. So even in a simple harmonic motion. Does every oscillation perform a wave? No, right? So like not every oscillation performs a wave, but for a wave to generate, there should be an oscillation. So this is not true, but the vice versa is true. Right? Like, not all oscillations produces waves, but waves are produced by oscillations. Any kind of waves, if you consider, mostly they are going to be based on a certain oscillation, right? A certain oscillation, except for the electromagnetic things and also those things we will see under optics. The general things that we deal with, most of the cases, for a wave to generate, you need to make an oscillation. So that doesn't mean all the oscillations produces waves. Right? Yes. Okay. So fine. I guess that's clear. Fine. Yeah. Let's move on. So write down below that. Write down. If a particle performs a repeated motion, if a particle performs a repeated motion within a simple linear track, within a simple linear track within equal time intervals, it is defined as a simple harmonic motion. A simple harmonic motion. Simple harmonic motion. So let's consider some examples of simple harmonic motion, right? Okay, I'll leave it as this, and it should be easy for us to analyze them. So let's consider some examples of simple harmonic. So now remember, we are talking about what? Simple harmonic motions, right? So like let's not write the topic and all. So I will write the topic in a while, right? So when defining, when we come into the theoretical definitions and all. So just when we talk about the general idea. So now we are talking about simple harmonic motions. So we are talking about simple harmonic motions. So let's consider some examples of simple harmonic motions. Some examples of simple harmonic motions, right? So the first and foremost, the most popular example is the motion of a simple pendulum, right? So the motion of a simple pendulum is the most frequently used example. It moves towards the right and stops here. Once again, it moves to the left, to the center point, Once again, from here it moves to the left, right? So it's a very simple oscillation, right? Very simple oscillation. It moves r distance to the left, sorry, right. Once again returns back. Once again moves r distance to the left. Once again returns to the center point, the mean position. The mean position within equal time intervals. Within equal time intervals, which means this can be considered as a simple harmonic motion. Right? Simple harmonic motion. So remember that I will be theoretically proving the simple pendulum, the motion of a simple pendulum to be as a simple harmonic motion. Later, later under simple pendulum. First of all, we will have to prove the motion to be a simple harmonic motion. So, guys who are doing maths and all, they might know how to prove a certain oscillation to be as a certain motion to be as a simple harmonic motion. They do know, but others no. Anyways, it's there in your syllabus to know how to prove these things. Prove means you are not going to prove in maths and all. Actually, that's simple questions, simple examples. Right? So you need to know how to prove these things. Let's learn that later, right? So for the time being, let's get the general idea since it's still the basics. So this is one example, right? So the simple pendulum, right? So what else? What else? What can be another well-known example? A helical spring. Have you guys heard about helical springs? Spiral springs. Yes. So if there is a spiral spring, right, and if it is at equilibrium at this kind of a position, right? If it is at equilibrium at this kind of a position, so okay. So this is at rest now. So now what I do is I will drag this x distance down. I will drag this x distance down. So what will happen if I leave? It will move up. Once again, it will move up the same x distance. Return back. It will keep on performing a simple harmonic motion. Right? Moves x distance, returns x, moves minus x, returns x. It's a very simple form of oscillation. So therefore, we can consider this once again as a oscillation, simple harmonic motion, practical, according to practical situations. Right? So even this we need to prove this theoretically. Right? And another example is what is this? This is a tuning fork. Tuning fork, right? So this is the arms of the two arms of the tuning fork. So if you just make a small vibration in one arm, it will vibrate in this direction. Right? It will start vibrating. Right? Even that oscillation is a very simple oscillation and can be considered as a simple harmonic motion. Right? So yes, you need to have what kind of motions can be considered as simple harmonic motions. Right? So have the general idea. So after this, taking down these examples, let's straight away move on to simple harmonic motion, the main topic. Right? Yes. Below that, write down from where you stopped. Example 1. Example 1. Example 1. A very long string, where one end is connected, where one end is connected, where one end is connected to a pendulum bob, to a pendulum bob, to a pendulum bob, is given a small displacement, is given a small displacement then the resultant motion will be, then the resultant motion, then the resulting motion will be, then the resulting motion will be a simple harmonic motion, a simple harmonic motion, a simple harmonic motion. Right? When you give a small displacement to this, it will perform a simple harmonic motion. Right? So yes, you can draw this. Just jot this down. Only this figure. Right. I guess that's done. So below that, example 2. Example 2. Example 2. The resulting motion, the resulting motion, the resulting motion of a helical spring, of a helical spring, of a helical spring, when it is dragged down, when it is dragged down and released, and released, when it is dragged down and released. Yes, you can draw. It's a simple harmonic motion. Third one. So you can draw this, right? You can take your time. Yes, I guess that is done. Example 3. Example 3. Write down vibration of a tuning fork. Vibration of a tuning fork. Vibration of a tuning fork. Take this figure. Vibration of a tuning fork. Vibration of a tuning fork. right? So guys, up to this extent, what we studied was just the basics, right? So it's, I don't know, it's not that important, but from now onwards, it's completely very much important, right? So like all the information, each and every word that I'm going to say is very, very important because it's a main topic, simple harmonic motion. So it's like this. Now we know this is in Sinhala, it's called Sarla Anuvarti Chalite. Like I will keep saying these things because there's no review books in Sinhala like English and all, right? So when you are supposed to go through like review books, I mean like so like there's review books of past papers, right? So most of them are going to be in Sinhala. So if you can read Sinhala and all, if you read and write, so it's perfectly fine. You can refer them, right? So when referring them, you need to know what the words are, main words are. So therefore, like, jot them down also. Sarla Anuvarti Chalite. Simple harmonic motion. Anyways, so one recommendation is like Dr. Rosa's. You guys might be already going through them. So Dr. Rosa's review books. Make sure to analyze those things, right? So if you need the PDF copies, let me know. I have the link from 1994 to 2019, right? So books, all the books, right? So in a drive. So just if required, let me know. I will send you, right? Yes, simple harmonic motion, right? So now we know what kind of motions are going to be simple harmonic motions. We know what kind of motions are going to be simple harmonic motion. Now, what we are going to do is we're going to get some expressions. We're going to get some equations to deal with a simple harmonic motion, right? So to deal with linear motions, we have a certain set of equations. To deal with projectiles, we have a certain set of equations. To deal with circular motions, we have a certain set of equations. Rotational motions, we have equations. Similarly, we also need equations to deal with simple harmonic motions. That, of course, we will have to derive and obtain, right? We're going to derive them. Right? It's very easy to understand the derivations and all. Simple derivations are there. So to know this, to understand this perfectly, you guys need have, y'all are supposed to have a prior knowledge on circular motion. So that is why on the first day itself, on the start of the group, of course, I sent you guys the circular motion note because y'all need it here. Right? Even if you are not okay with circular motions, that's fine, right? So forget about the derivations. At least try to remember the equations. But if you can remember how these things are derived, it's going to be like very easy for you to use. The usage is going to be easy. So you know how these were derived and where to apply and how to apply them, right? So yes, understand what I'm going to say now perfectly. Yes. So it's like this. To derive to derive equations for a simple harmonic motion, we make use of a circular motion. We make use of the circular motion. It's like this. Let us consider a particle. Let us consider a particle which performs a circular motion. Right? Let's consider center. This is the center. This is the center. And this is the particle. Let's assume this is the particle. Let's give it a name as P. Particle P. Particle P. Right? So I will divide this into 4 quadrants. So it's easy work, right? So not a big task. P. This particle is P. Correct? Now let us consider when this particle moves from okay, this is particle P, and the projection of this particle P on the y-axis, if I consider this as the x-axis and this as the y-axis, if I consider this as the x-axis, this as y-axis, the projection of particle P on the y-axis, let us assume it to be as Q. Let us assume it to be as Q. Q. So when P moves from point A to B, this is O, right? When P moves from A to B, when P moves from A to B, when P moves from A to B, Q moves from O to B. The projection. If you see from this side, the projection. Projection means like when this is projected to Y. Right? It's like here. This is P, this is Q. When P moves from A to B, the particle Q moves from O to B. When P moves from B to C, when P moves from B to C, what happens for the projection? So it was like this. Now, this is P. P moves from B to C. What happens to the projection? So when P moves from B to C, Q, the projection of P, the Q moves from B to O. If any one of you guys have any issues, let me know. I'll repeat once again. Right? When P moves from C to D, when P moves from C to D, Q moves from O to D. When P moves from C to D, Q moves from O to D. When P moves from D to A, when it moves from D to A, the Q moves from D to O. Yes, P is the particle and Q is the projection. P is the particle and Q is the projection. Right? Particle projection. Right. So, why did I do this? If you see this, when P performs a circular motion, when P performs a circular motion, Q performs what? Q performs, goes from O to B. Once again, returns back from B to O. B to O, once again goes from O to D. O to D, once again returns back. So when P performs a circular motion, Q performs what? Q performs an oscillation. Q performs, the projection performs oscillation. The projection performs an oscillation. So this is a very good relationship for us to get some expressions for the simple harmonic motion, because this is a simple harmonic motion. A simple harmonic motion. Yes, I guess that's clear. So now I'm going to make use of that. Make use of this behavior. Right? So I'm going to make use of this behavior of Q. So now let us consider a situation where P is somewhere here. P is somewhere here. P is somewhere here. From here it has moved to this point. Right? Right. So P moving from here to here means it has covered what? It has covered an angular displacement of theta. It has covered an angular displacement of theta. So don't ask me what is angular displacement, because it's circular motion, right? I guess you guys are okay with that. For the derivations, if that is unclear, just bear it up, right? Theta. So P, what, like when P performs from here to here, it has covered theta distance, theta angular displacement, right? So the projection is where? The projection is here. It should be here, right? The projection on y-axis should be here. So when P performs angular displacement of theta, the Q particle performs a linear displacement. Let's call it as y. A linear displacement of y. A linear displacement of y. When this performs covers an angular displacement of theta, the particle Q will perform a linear displacement y. So we are going to find expressions for the displacement. This displacement y. We're going to find an expression for the displacement y, the displacement of simple harmonic motions, the displacement of simple harmonic motions, displacement of oscillations. Right. So just the basics. P performs what? Circular motion. P performs circular motion. So this will be the tangential velocity. This will be the tangential velocity. Tangential velocity V, and angular velocity omega. So when P is performing a circular motion, it will have a tangential velocity V and a angular velocity omega, right? So those things are known. And if this is the radius, we can deal with it, right? So yes, what are the required things? If this is S, if this arc length is S, we can write S is equal to R theta. So these are the equations corresponding to circular motion, right? Circular motions. I hope you guys are okay with that. S is equal to R theta. And also we can write what? V is equal to R omega. This tangential velocity is equal to R times omega. r times omega, and then tangential acceleration. The tangential acceleration at is equal to r alpha, right? Tangential acceleration, which let's not, we might not require that, but still the radial acceleration is in which direction? When the object is performing a circular motion, the radial acceleration is towards the center, always towards the center. That is why we call it as a radial acceleration, right? So I guess you guys are okay with that. So A is equal to r squared omega. Omega squared r. Omega squared r. So what is time taken to perform one complete revolution is what? Time taken by P to perform one complete revolution is what? T is equal to 2π divided by omega, right? And omega is equal to theta divided by T. Those things are there. And okay. And omega. What is omega? Angular velocity. Angular velocity is the rate of change of angular displacement. Which means angular displacement is omega t. So these are the tools. That we might need when you deriving equations for the particle Q, the simple harmonic motion of particle Q. We are going to derive what? Equations for the simple harmonic motion of particle Q. Right. Okay. Fine. So, first of all, my first goal is to find the now these are for the simple harmonic motion. Now these are for the simple harmonic motion of Q. I'm going to find first of all an expression for the displacement, of simple harmonic motion, y. I'm going to find an expression for the displacement. Very easy. What is y? Y is equal to, this is r. Y is what? R sine theta. This is theta. R sine theta. It's a very small thing. Right? So y is equal to r sine theta. Theta is what? Omega t. Theta can be written as omega t. But theta is omega t. Therefore, y is equal to r sine omega t. Y is equal to r sine omega t. So I have an expression for the displacement of the simple harmonic motion. I have an expression for the displacement of the simple harmonic motion. It's very small thing, right? So easy. So now I will make use of this space to write down all the equations that we gathered. Y is equal to r sine omega t. Y is equal to r sine omega t. Now we have got one equation that is for what? Of simple harmonic motion, that is for displacement of the simple harmonic motion. Now I'm going to get another equation for the velocity of the simple harmonic motion. For the velocity of the simple harmonic motion. I'll assume this q particle is having a velocity of vq. I'll assume the simple harmonic motion, that the particle that performs the simple harmonic motion has a velocity of vq. Right? I'll assume this has the tangential velocity of vp. Velocity of p. You can directly relate the velocity of p and q, because both these guys are moving at the same time together. Both are moving at the same time together. So now what you need to see is what factor of p's velocity is affecting q. You need to see what factor of p's velocity is affecting q. Okay, vp, if this is theta, this is theta. This is theta. This is 90 minus theta. This is theta. This is 90 minus theta. Why? Tangential. Tangent and radius is always 90 degrees. And then once again vertical, 90 degrees. So if this is 90 minus theta, this is theta. Theta, 90 minus theta. So you can resolve this VP cos theta, VP sin theta. VP cos theta, VP sin theta. So think about it. Is VP sin theta going to affect this Q? Is VP sin theta going to affect Q? No, because Q is moving vertical. This is in the horizontal direction. So what affects Q is the vertical component. What affects Q is vertical component. So VQ is VP cos theta. Velocity, right? VQ is VP sin theta. VP sin theta. Sorry. VP cos theta. VP cos theta. Cos theta. Do we know cos theta? No, we don't. No, we don't. If this is theta, this is theta. This is R. This is Y. This is R. This is Y. Right? So this is R. This is Y. Can't I find this? Pythagoras. Simple, right? Pythagoras. R squared minus Y squared square root. R squared minus Y squared square root. So now you can write an expression for cos theta. What is it? Cos theta is equal to what? Adjacent over hypotenuse. Adjacent over hypotenuse R. So therefore VQ is VQ is VP cos theta is what? R squared minus Y squared over R. What is VP? VP can be written as tangential velocity can be written as R omega. R omega. VP can be written as R times omega. So here write it. So V, I'll mark this VQ as V. V is equal to VP is what? R omega R squared minus Y squared over R. So R to R cancels. So V is equal to omega R squared, omega squared, right? So here this is R omega. So omega R squared minus Y squared. So I have what? I have an expression for displaced. I have an expression for the velocity of the simple harmonic motion. I have an expression for the velocity of the simple harmonic motion. Now I have displacement, an expression for the displacement, and an expression for the velocity. So very important. Complete oscillation is going to be depending on this and this and the acceleration, the expression that I'm going to get for the acceleration. So I will not get it straight away because like y'all might need some time to process. So was it clear up to this point? Any insight? Any issue? Was it clear? Yes. Okay. Others also, I assume it's clear, right? Yes. Is there? Yes. Nice. Right. Okay. Nice. Okay. Fine. Okay. So I think let's take down the topic. And yes, nice. Okay. And then let's compare it up to this point. And let's take just 5 minutes of a break. Right. So like 3 hours continuously. If we keep on, if you guys are in front of the screen, so it's not going to be once again effective. Right? So like I need this thing to be 100% clear and perfectly done, right? So yes, let's take these things down and let's take a small break, right? 5 minutes. Simple harmonic motion. So write down simple harmonic motion. Simple harmonic motion. Main topic: simple harmonic motion. Simple harmonic motion. Below that, write down. Consider a particle capital P. Consider a particle capital P. Consider a particle capital P which performs. Consider a particle capital P which performs a circular motion. A circular motion with constant angular velocity. With constant angular velocity. With constant angular velocity. With constant angular velocity. Omega, within bracket, omega. When, full stop, when capital P performs a circular motion, 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 the projection of P the projection of P, the projection of P on the y-axis, on the y-axis, on the y-axis, which is Q, which is Q, which is Q, will perform a simple harmonic motion. Will perform a simple harmonic motion. Right? So I need you guys to draw this, write this down, and then this, and then prove this. Okay? So, and then we can take 5 minutes break. So we will once again start at 4:40. At 4:40, need to complete this and take 5 minutes break. Right? So I know it's too much. We'll be doing up to 5, 6, 10. Right? So compensate, will be compensating that also, because like time is very important, right? So yes, I think you can take a small break until 5:40, 4:40, right? In the meanwhile, take these things down also. I guess y'all are back. I hope y'all took a small break, right? So yes. Anyways, yes, let's continue, right? We have to prove acceleration. So I will, for that, of course, I will take up some space from, I'll erase this. I hope you guys wrote it down, right? So I will erase this portion and I will use that. Or else I could use this portion also, right? This, the below part. I'll use this. I'll use the below part, right? Acceleration. Acceleration. So how do we write acceleration? How do we get an expression for the acceleration of the particle Q? So it's like this. So we need to see what factor of the acceleration of P affects the Q. So you need to see, because like both are moving together at the same time. We need to see what? We need to see what factor of the acceleration of P, what factor of the acceleration of P is affecting the acceleration of Q. So what is the acceleration of P in the first place? I mentioned you in the first passage itself, this is a constant angular velocity. The P performs a circular motion with constant angular velocity. If it performs a motion with constant angular velocity, does it have a tangential acceleration? Does it have an angular acceleration? No, no angular accelerations. If you have learned circular motions thoroughly, you'll know. If it is having a constant angular velocity, it's not going to have a angular acceleration, which means it's not going to have a tangential acceleration. But definitely, if it performs a circular motion, any object that performs a circular motion will have a centripetal acceleration. Will have a centripetal acceleration. Any object that performs a circular motion will have a centripetal acceleration. Acceleration towards the center. Acceleration towards the center. We call it as radial acceleration also. What is it? A. I'll call it as AP. Acceleration of P. No, I'll call it as AR. Okay. Because why? To denote it as radial acceleration. AR. So of AR, what factor affects Q? Is AR cos theta going to affect Q? Is AR cos theta going to affect Q? Because Q is moving in vertical. So what affects Q is AR sin theta. AR sin theta. It is moving upwards. AR sin theta is acting downwards. AR sin theta. Is AR cos theta going to affect Q? Because Q is performing a vertical simple harmonic motion. But what affects is AR sin theta. Right? So what affects Q is the acceleration on Q is AR sin theta. Sin theta. AQ is what? AR What is sine theta? Sine theta. What is sine theta? From this you can get sine theta. What is sine theta going to be? Opposite over hypotenuse. Opposite is y, hypotenuse is r. Opposite over hypotenuse. Opposite over hypotenuse. Y over r. Y over r. Y over r. Right? Which means AQ, I'll commonly call it as A. Acceleration acting on Q is A. It is AR means what? AR means omega squared r. Omega squared r into y over r. Into y over r. So r to r cancels. A is equal to omega squared y. A is equal to omega squared y. A is equal to omega squared y. Is this correct? The acceleration acting on particle Q. Is it correct? Think about it. No. Because Q is moving upwards, acceleration is acting downwards. Acceleration is opposite to the direction of motion. If an acceleration is opposite to the direction of motion, there should be a minus. There should be a minus thing. So let's assume if a particle is moving forward, right, acceleration is acting in this direction. So for this particle, this acceleration is considered as a negative acceleration. In this direction, it's considered as a negative acceleration. Deceleration. The object is moving upward, the particle Q is moving upward, acceleration is downwards. So minus. It is directed towards the center. It is directed towards the center. So therefore, I included a minus mark. So now A is equal to minus omega squared y. Very important equation, right? So y is equal to omega r squared minus y squared. A is equal to minus omega squared y. So now we have equations to deal with a simple harmonic motion. We have displacement, we have velocity, we have acceleration. So it's a yes. So now since we have these things, we can deal with questions related with simple harmonic motions. Right? So yes, before we move on to that, so I guess that is clear. The acceleration, how I got the acceleration of a simple harmonic motion. Right? So you can take this down. Acceleration AQ equal AR sin theta. AQ is equal to AR sin theta. AR y over r. Sin theta is y over r. Y over r. A is equal to omega squared r. AR is equal to omega squared r. Y r cancel. And then due to the direction, opposite direction, minus. This will be the equation. So you can take this down. Right. Yes, I'll have written it. So below this, we need to explain why we wrote minus, right? So we need to have an idea of that, right? So yes, let's put a mark like a note, right? Note, write down note. Here, negative sign implies that. Here, negative sign implies that the acceleration is always acting in the opposite direction, for the increase of displacement. Comma, which means acceleration is always directed towards the center O, towards the center O of the simple harmonic motion. Right. So now we need to see at which points the velocity is maximum, at which points the velocity is minimum, at which points the acceleration is maximum, at which points the acceleration is minimum. Right. So to depict this, I will make use of an example. So rather than okay, we know this is a simple harmonic motion. I will not consider this anymore. So these derivations are done, right? So derivations are done. So you do not have to worry about the circular motions anymore. Right? You do not have to worry about the circular motions anymore. If you know these three equations, you can solve any sort of you can solve any sort of questions which you come across in oscillations. Right? So yes. So let us consider an example of a simple pendulum, and so if we need to see, so what is this R? What do we call this point R? R is the maximum displacement possible by a simple harmonic motion. Can a simple harmonic motion move as much as it wants? No, it can move a certain maximum displacement. So what is the maximum possible displacement? This. So it is y is equal to R. So R is what? R is called as the amplitude, right? So for the maximum possible displacement, we call it as amplitude. And this mean position, the origin, the mean position, we call this as the mean, yeah, we call this as the mean position, all right? Mean position slash equilibrium point. Equilibrium point. Remember, right? Mean position or equilibrium point. Y equals R. So if this is Y equals plus R, when it moves to the opposite direction, what is this? Y at this location, this is Y equals minus R. A, O, A, B. So I need you guys to understand that now we are going to analyze at which point the velocities are going to be maximum and at which point the velocities are going to be minimum first. Let's consider only the velocities first. So you know very well, and also you need to know that always in a simple harmonic motion, the displacement is measured from the mean position. You're not going to measure the displacement from here or else from here. Displacements are measured from the origin or from the mean position or from the equilibrium point. From the equilibrium point, like this. This is displacement. So what is the equation for the displacement? Y equals R sin omega t. Y equals R sin omega t. Right. So I need to see at which point the velocity is maximum. Right. Let's get the equation. Right. Velocity is omega what? R squared minus Y squared. So let's see what the velocity is at point O, at the mean position. What the velocity is at O. I'm going to see the velocity. What is the velocity at O? So what is Y? Y is, I told you, it is measured from O. So what is Y? No displacement, 0. Y 0. Therefore, apply V is equal to omega. R is amplitude. So apply Y. Y is what? 0. Right? So V is omega R squared. V is omega R. V is omega R. This is the maximum possible velocity. This is the maximum possible velocity. Why did I say it has maximum possible velocity? From this kind of an expression, what varies here? Is omega going to vary? No, omega is constant for a simple harmonic motion. Is R going to vary? R is given. When the simple harmonic motion takes place from point to point, what's going to vary is Y. Y. When Y is maximum, V is minimum. Think about it, because from a certain thing, you are subtracting Y. So when that subtracting term is maximum, this is going to be minimum. When this is minimum, the amount that is being subtracted is minimum, the remaining is maximum. So that is minimum there at Y equals at the center point. So at the center point, the displacement is 0. Therefore, this is what? V max. Whenever you are required to find the maximum velocity of a simple harmonic motion, it is not only true for this, right? So it's true for all the simple harmonic motions. whenever you are required to find the maximum velocity of a simple harmonic motion, straight away use this. Vmax is equal to omega r. Vmax is equal to omega r. Right. I will send you the tutorial maybe tomorrow. Right. So, and I will assign some questions. So I'll let you know how things are going to be done. Right. Vmax. Right. So this is the maximum velocity. The maximum velocity is given at which point? At the center point. Which means at the amplitude, the velocity is going to be just without applying any equations, you can figure it out. What's the velocity at the maximum? The pendulum will move to the maximum amplitude, it will stop, and then it will return back. If it stops at the amplitude, the velocity is going to be 0, right? If it like to turn other side, the particle should stop, and only it should turn back. Right? So it should go, it should stop. Once again, it should return back. So the velocity is minimum at which point? Here the velocity is 0 at the amplitude. So let's go at the amplitude. Where? How do we at r, at amplitude, at r. So let's use the equation. At r, y is equal to what? Y is equal to r. The displacement is r. When the particle is here, the displacement is r. So V is equal to omega r squared minus y squared. R squared minus y squared. So V is equal to omega. So r instead of y, you can apply r. R squared. R squared minus r squared is 0. Into 0 is V is going to be 0. So even you can theoretically show that the velocity is 0. At A, the velocity is 0. So you need to understand that at the amplitude, it will have the minimum velocity, while at the mean position, it is going to have the maximum velocity. For a simple harmonic motion, at the equilibrium point, it's going to have the maximum velocity, while at the amplitude, it's going to have the minimum velocity. So very important, because like a lot of questions are going to be given based on this point. Kinetic energy, a lot of energy and all related questions are going to be there. Right? So let's see how they are. Let's analyze them later. For the time being, you need to understand this. Right? So yes, I think you can quickly draw this and take this down. If there's any doubt, make sure to ask. Right? So, anyways, for 21, of course, the exams are not going to be on October, right? It's like most of the time. It's going to be on December, and also December is once again not quite sure they are, right? Some of them say it's going to be on January or something, but I don't think it will be on January. Somehow they manage it to conduct the exams, maybe even on the final week of December, right? So, but some of them are have mentioned that mostly it will be on January also, right? So that's a possibility, it seems, because they have not yet sent any admissions and all. I mean, the applications and a lot of things are there, right? So, anyways, try to get things done before December, right? So even if you get one more month in extra, yeah, make use of it, right? So, without considering it as a burden, even that month, you need to make use of it, right? So even for 22, of course, it's going to be there on 22 December. If there's more waves and all, once again, even they are going to have it on later, right? So, for these exams to be delayed and all, it's not only the COVID situation, right? So a lot of other things, external factors are there. For example, so in our faculty, of course, that's around two batches which have never seen the university yet. Like, so they have got selected, got through to engineering, and then they have never seen the university yet. Right? But still, they have covered around 2 semesters online. Right? So online 2 semesters are done, which means first 1 year is done. Right? So first year without even seeing the faculty. Right? So I don't know. That's how things are, right? So, anyways, a lot of things are there. So, like, a lot of factors are there. So, make use of the time that you have, right? So, yes, it has. Okay, so we know that. I think it's done. Okay? So, I think it's done. So, if not, while I read out this thing, so you can leave a small space if it's not done. Write down below. When a simple harmonic motion is considered, a simple harmonic motion is considered, the maximum velocity of the particle will be given at the mean position. Write down within bracket V max is equal to omega r. V max is equal to omega r. While, close the bracket, while the minimum velocity of the particle will be given at the amplitude. While the minimum velocity of the particle will be given at the amplitude. In brackets, velocity equals 0. In brackets, velocity is equal to 0. Right. Let us see at which point the acceleration is maximum, at which point the velocity acceleration is minimum, right? So yes. So when you analyze acceleration, what is the equation that you need to know? A is equal to minus omega squared y. So when you are dealing with the magnitude of the velocity acceleration, make sure to omit the negative sign. You need to understand this point well. when you need to get an idea of the magnitude of the velocity, you do not have to deal with the minus sign. Right? So omit it. This straight away gives the magnitude. Right? So we need to see where the magnitude of the acceleration is high, like highest and the lowest. Forget about the minus sign. Right? So this is very easy to analyze, because why? Omega is constant. Omega is constant. Omega is constant. Therefore, acceleration is directly proportional to y, right? So this is constant. Therefore, acceleration is directly proportional to y. Therefore, acceleration is directly proportional to y. When y increases, when the displacement increases, acceleration increases. When the displacement increases, acceleration increases. Right? Which means the maximum acceleration, A max, is given at where? Is given at y max. A max is given at y max. So y max is what? What is the y max? Y max is r. Which means A max is given at the amplitude. Amplitude is given at the amplitude. Amplitude. Right? So you can apply amplitude. So A max is equal to omega squared. What is the amplitude? R. Omega squared R. This will be the maximum acceleration. Maximum acceleration. Okay. So we know where the maximum acceleration is going to be given now. The maximum acceleration is going to be given at where? At the amplitude. At the amplitude. Right? At the amplitude. At the amplitude. So we need to see now where the minimum acceleration is given. Where the minimum acceleration is given. Right? Let's see. To find that out, we can once again use this. When A is minimum, when y is minimum. A is minimum when y is minimum. So what is the minimum y? The minimum possible displacement. The minimum possible displacement is 0. Y equals 0. Right? Therefore, A mean at center point. A mean at center point. Which means A mean is omega squared into 0. Right. Omega squared into y equals 0. 0. Which means A mean is 0 is given at this point. Right? So the minimum acceleration is given at the equilibrium point. So you need to know, this is kind of confusing, right? So you need to get that clear, because at the center point, the acceleration is minimum, velocity is maximum. At the amplitude, acceleration is maximum, velocity is minimum. Velocity is minimum. Right? So this is the beauty of simple harmonic motion. It has a characteristic. And usually other motions, whenever the acceleration is maximum, velocity is maximum. Whenever the acceleration is minimum, velocity is like that kind of a thing, right? So but here it's completely opposite. Right? So velocity is maximum when acceleration is minimum. Acceleration is maximum when velocity is minimum. Right? So you need to understand that. Right? Okay, I guess that is clear. Right? Quickly take this out. So if you all missed any part and all, so don't worry, because like I'll be giving you the recording also in that purpose that you can clarify. It's like fill that up, but make sure to write them quickly. Right? So uh, I guess yeah, that's done. Right? So below that, like since this all these things given, I think we do not have to write down that amplitude. This is maximum and minimum, right? So you can figure that out. Right? So okay, so I'll move on to the next important part. This is once again very very important, right? So yes, that is we are going to see the characteristics of a simple harmonic motion. We are going to see a characteristic of a simple harmonic motion. Constant, then tangential acceleration is 0. When yes, exactly, tangential acceleration is 0. When the angular velocity is 0, when the angular velocity is constant, tangential exactly, right? So when there is a particle, if it performs, if the tangential acceleration is 0, which means in the tangential direction the velocity doesn't increase. In the tangential direction the velocity doesn't increase. There is no increase in the velocity in the tangential direction. Each position is v. Each position is v. All the position is v. Right? So if v doesn't increase, if v doesn't changes according to v equal r omega, if v doesn't changes, omega doesn't changes. So omega doesn't changes. Simple. Right. Okay. Fine. I guess that's clear. So you need to understand that there are some characteristics for a simple harmonic motion. So that of course we are going to analyze step by step. Right. So the characteristics of a simple harmonic motion. Right. Characteristics of a simple harmonic motion. Right. So I'll consider it as definition. So I told you I will define the simple harmonic motion theoretically. If this happens and if this happens, then only a certain motion can be considered as a simple harmonic motion. Theoretical definition. Right? So this is the theoretical definition. That is A equal minus omega squared y, right? Omega squared is a constant. omega squared is a constant. You know, omega, I told you, because when the circuit, when the corresponding P performs a constant angular velocity, it has a constant angular velocity. Therefore, this also has a constant angular velocity, right? Constant. If that is the case, A is directly proportional to Y. A is directly proportional to Y. So, based on this equation, you can define what a simple harmonic motion actually is. Based on this single equation, you can define what a simple harmonic motion is going to be. Right? That is, acceleration. Simple harmonic motion is a type of motion where acceleration is always directed towards the center. This minus denotes what? The acceleration is always directed towards the center. If it moves in this direction, acceleration towards the center. And if once again, when it is coming in this direction, once again acceleration towards the center. Going in that direction, acceleration towards the center. Once again, when it returns back, acceleration towards the center. Always the acceleration is directed towards a fixed point. First thing is, for a motion to be a simple harmonic motion, first condition is the acceleration should always be directed towards the center. Towards the center. Right? Directed towards center. How did you get that point? From this minus. From this minus. Right? So whenever the displacement increases, acceleration towards the center increases. Right? Acceleration towards the center increases because minus. That is the first thing. The second thing is, if a motion is supposed to be considered as a simple harmonic motion, the acceleration will be directly proportional to the displacement. Acceleration directly proportional to the displacement. Directly proportional to the displacement. So, if a certain motion satisfies these two conditions, that motion can be considered as a simple harmonic motion. Simple harmonic motion. Even in combined maths, what you do is, it doesn't matter what the question is. You simplify and show that the acceleration is directed. You simplify and bring it to this kind of an equation, characteristic equation. So the long story in short is, if you need to show a certain motion as a simple harmonic motion, you need to prove that the acceleration of that particle has this kind of a format. Has this kind of a format. Say not this kind, like has this kind of a format. This is not always supposed to be omega squared. So it can be a constant. Acceleration of that particle should be equals minus constant y. Then only we can say due to this minus, Acceleration is always directed towards the center, and this is a constant, so therefore acceleration is directly proportional to the velocity. Then only you can define that motion as, consider that motion as a simple harmonic motion. Right? So the simple harmonic motion is basically a motion which has these two properties. This is the theoretical definition of simple harmonic motion. This is the theoretical definition of simple harmonic motion. Okay. So very, very important. Right. So if you need to show that this simple pendulum is performing a simple harmonic motion, you need to prove that the acceleration of this pendulum bob is having this kind of a characteristic. If you need to show a helical spring is performing a simple harmonic motion, you need to show the acceleration of the spring is directed by this kind of a. That is the basic idea. Right? That is the definition of a simple harmonic motion. I guess you understood. Right. So let's write that down. Right. So let's write it down. Write the topic definition. 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 The topic definition. Write this down. A is equal to minus omega squared by. A is equal to minus omega squared by. A is equal to minus omega squared by. Omega squared is a constant. Omega squared is constant. Is a constant. Is a constant. Omega squared is a constant. Therefore, A is directly proportional to Y. A is directly proportional to Y. Write down first one. Not the first one. So below, write down. If a particle performs, a simple harmonic motion, then comma, first number, first characteristic, the acceleration of the particle will always be directed towards a fixed point. Within bracket, equilibrium point. Within bracket, equilibrium point. Second point, the acceleration of the particle will be directly proportional to the acceleration of the particle will be directly proportional to the displacement to the displacement from the fixed point, from the fixed point. Within bracket, A directly proportional to Y. A directly proportional to Y. All right. So let's go for the next thing, that is the time period. What the time period means. Let's see what. I'll write it below. Let's see what time period is. What is the time period? If you have analyzed circular motion, you know time period is the time taken by the particle P to perform one complete revolution. So what is time period T? If it starts at T equals 0, the time taken by the particle P to perform one complete revolution. The time taken by the particle P to complete one revolution. When P performs a circular motion, Q performs what? When P performs a circular motion, Q performs what? An oscillation. So the time, so what is the time period for an oscillation then? What is the time period for a simple harmonic motion? The time taken by the particle Q to perform one complete oscillation. So the time period for a simple harmonic motion is defined as how? The time taken by the particle to perform one complete oscillation. If it started at T equals 0, it should reach the same point at T equal capital T. Then only one oscillation is done. What will be this T? What is the T here? What is the time period for a circular motion? That you know. T is equal to 2 phi divided by omega. How did I get this? From for P, I'm going to apply what? Omega is equal to theta divided by T equation. Circular motion equation, right? So angular velocity equation. Omega is equal to theta divided by T. What is omega? Omega is omega, right? So angular velocity. Theta is what? When it performs one complete revolution, theta is going to be 2 phi radians. What is going to be the time taken? Capital T. So time period is equal to 2 phi divided by omega. So now I'm going to find the time period of an oscillation. How am I going to find it? By using the circular motion. So all the other equations was also found in the same way, right? By using the circular motion. Think about it now. are they going to have the same time period or different time period? When P performs one complete revolution, Q performs one complete oscillation. P and Q will take the same time to perform their respective motions. When this performs one complete revolution, Q will perform one complete oscillation. Therefore, time period for Q is what? The time period for Q is capital T is equal, once again, 2π divided by omega. 2π divided by omega. Right? So another equation. We have another equation for simple harmonic motions. For simple harmonic motions. So I guess that is clear. Right? So both takes the same time. Right? So they have the same time period. The oscillation and the revolution has the same time period. P and Q has the same time period. Right? Yes. I guess that's clear. So yes, write down the topic time period. Time period. Time period. Below that, write down. Below that, write down. If capital T is the time taken by the particle P, if capital T is the time taken by particle P to perform one complete revolution, comma, the same time capital T, will be taken by particle Q to perform one complete oscillation. You can quickly draw this and write this. Just draw this and write this. Okay, so that is done. So what is the time period taken by this oscillation? If it starts at 0, t equals 0, it should move here, 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 and here. Then only one time period. The time taken to make this complete motion is considered as the time period, right? So yes, that's fine. So now let's see what a frequency is. What frequencies? Let's see what frequencies. Let's see what frequencies. In circular motion, we did not deal with frequencies. Instead, what we dealt with was rate of revolutions. If you remember, rotations per minute, rotations per second. Similarly, here in an oscillation, we deal with not rate of revolution. So because oscillation is not going to oscillate. It's not going to perform revolutions, right? So it's going to perform oscillations. So we are going to deal with frequencies. Frequencies. So frequency means, so what is time period? Time period means the time taken to perform one oscillation. Frequency means the oscillations performed in the number of oscillations performed in 1 second. Number of oscillations performed in 1 second. Understand the difference, right? Frequency means the number of oscillations performed per second. So if in 1 second, if I on the stopwatch, if this performs 5 oscillations in 1 second, the time period is 5 hertz. Sorry, not the time period, frequency. Sorry, frequency. Right. Frequency is 5 hertz, right? So what is the equation what it's going to have? Sorry, in capital T time period, how many oscillations will it make? 1 oscillation. So that is the definition of time period, right? Time period is the time taken to perform 1 oscillation. Right? So let's see how many oscillations it will make within 1 second. In 1 second, how many oscillations? 1 over t. In 1 second, how many oscillations? 1 over t, which means this is frequency. Frequency is equal to 1 over t. Frequency is equal to 1 over t. 1 over t. 1 over t. Okay? So the equations for frequency is 1 over t. 1 over time period. 1 over time period, right? So how did I get that? So you know, in this time period, the number of oscillations performed is what? 1. What do I need? So what is frequency? The number of oscillations performed in 1 second. So in this side, it's time. Number of oscillations. In time t, capital T, 1 oscillation. In 1 second, 1 over t oscillations. 1 over t oscillations. And units is what? Units of frequency is 1 over second gives you per second, or else it's represented as hertz. Per second for the convenience purpose, is represented as hertz. Hertz. Right? So that is pretty much it for frequency. So therefore, frequency is what now? Frequency is 1 over T, 1 over capital T. Frequency is 1 over capital T. So also we know T is what? T is 2 pi over omega. F is 1 over T is what? 2 pi over omega. 2 pi over omega, which means omega will go up. Omega will go up and 2 pi. It gives you omega is equal to 2 pi F. Omega is equal to 2 pi F. A derived equation. So like you can remember this if you know the circular motions properly. That is omega is equal to 2 pi n. In that case, rate of revolutions. Don't mix up, right? Simply omega can be written as 2 pi F also. Omega can be written as 2 pi F also. Just remember that. Right? So the main thing is this. I guess that's clear. Right. So write down frequency. 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 Below that, right? If the particle Q performs one oscillation, if the particle Q performs one oscillation within a time period capital T, within a time period capital T, then the number of oscillations, per unit time, in bracket 1 second, is defined as frequency. So write these things down. T1 1 over T frequency units, and this equation is. So yes, that will be it for the theory for today. We have covered up to frequency, right? So let us do one example question, theory question, which is based on these things, right? So the things that we learned today. Okay? So just a small question, right? So yes, write it down. So example 1. I guess this is done, right? So example 1. Let's wind up by doing one example, small question, right? So in the theory note itself, write down example 1. Example 1. Consider a particle. Consider a particle performing a simple harmonic motion. Consider a particle performing a simple harmonic motion with an acceleration a equals 25, right? 20 a equals minus 25 pi squared y. With an acceleration a equals minus 25 pi squared y. Full stop. Find first question, time period. Second one, frequency. Third one, if the amplitude equals 10 centimeters, find maximum velocity. Find maximum velocity. Right. So let's see how to analyze this kind of a question. It's a very basic question, right? So nothing is there. Right? So the saying a particle is performing a simple harmonic motion. It's performing simple harmonic motion. If it is performing a simple harmonic motion, it should have an acceleration. And that acceleration is going to be what? It's going to be this. A is equal to minus 25 pi squared y. So what is the characteristic equation of a simple harmonic motion? What is the characteristic equation for the acceleration of a simple harmonic motion? A is equal to minus omega squared y. This is the characteristic equation for the acceleration of a simple harmonic motion. Which means when you compare this, a minus omega squared should be what? 25 pi squared. So omega is equal to what then? Omega squared is 5 pi whole thing squared. I can write 25 pi squared, 5 pi squared. So omega can be written as square to square cancel 5 pi. Radian per second. So I need the time period. So how do I find the time period? Time period is equal to 2 over omega. T is equal to 2 phi. Omega is what? Pi 5. So this to this cancels. T is equal to 2 divided by 5, right? So this is going to give us what? 0.4, something around 0.4 seconds. The time period, the time taken to complete one whole oscillation is 0.5 seconds. Just by looking at this, we got this. Right. I guess that's clear. Let's find the frequency now. Frequency. How do we find the frequency? F is equal to 1 over T. Is equal to 1 over T. Frequency is equal to 1 over time period is what? 0.4. 0.4. Right? So this will give you 2.5 hertz. 1 over 0.4 when simplified, it's going to give you 2.5 hertz, which means per second, how many oscillations? 2.5 oscillations. In 1 second, 2.5 oscillations are performed. Right? Third one, they have given the amplitude. R is equal to 10 centimeters. They are asking the maximum velocity, Vmax. So what is Vmax? Vmax, we wrote in the theory. Vmax is equal to omega R. This is the equation for velocity, but we have another equation for Vmax. Let's write that also. Omega R. Omega R. Vmax. Omega is what now? Omega is 5.5. 5.5. Radius, not the radius. Amplitude is what? 10 into 10 to the power minus 2. Right? So Vmax is going to be 0.55 meters per second. 0.55 meters per second. You can substitute pi and simplify if required. Right? I'll just leave it as it is. Right? So yes, this is pretty much it. Like you're going to get these kind of questions, and then like these equations, these set of equations could be used to solve a lot of difficult questions. I will be sending you the tutorial maybe tomorrow, right? So today, of course, I will not have some time to find it. It's going to be in the drive, right? So I'll get it and then I'll send you, right? So yes, yeah, you can take this down. The workout. So workouts of theory questions are going to be taken down, but tutorial questions, when solving them, then I'm going to waste much time on writing the same thing which is on the board in the note. Right? So we'll be getting a photo and I'll be sending you that after the class. Right. I guess taken down. Yes. So this is pretty much it for today's session, right? We will meet on the next session then and start from. So next on the next session, of course, we have to do graphs of simple harmonic motions and phase angles. Yes, phase angles and graphs, right? So that will be it. And then if time permits, I'll be moving on to energy of simple harmonic motion also. So, and before moving into energies, we'll be doing the tutorial also, right? So the tutorial discussion is also there. I'll send you the tutorial within a day or two, right? So, and then I'll instruct you guys to try some questions out based on today's, like, of course, we did not do a lot of questions today. But on the next session, so like after a certain amount of theory is covered, let's straight away go to the tutorial and cover them, right? So I will send you the tutorial within a day or two, right? Yes, so that is it. And then if there is any feedback and all, if you guys like to increase the speed, and or else if you need to decrease the speed, or else like whatever it is, if there's anything, you can personally let me know. So like yeah, that's fine, that's perfectly fine, right? So we'll see how it's going to be done. And okay then, guys. And so like, did you understand today's session? Was it clear? How about it? Was it confusing or was it clear? Yes. Okay. Right. Okay. Nice. I guess others also understood today's session. So therefore, right. Okay. So anyways, I will wind up the session then. And thank you, guys. So I will say, and also I will send you the recording, right? So make sure not to share with others, right? So make use of, like, if you need, you can make use out of it and then like download and all. But like, let's minimize that, right? So, like if there is anyone who would like to join, like they can join, but still let them contact me in the first place, right? So don't share these things. I'm doing this for your benefit, right? So yes, I guess I understood, right? Okay, thank you then, guys, and thank you, right? See you. Okay, bye.